Okay, welcome everyone. We're very happy to have Nicolas Garcia Trillos speak this week. So Nicolas is a assistant professor at Wisconsin-Madison. Before that, he was I'm not sure I know the correct pronunciation, but the Praga assistant professor at Brown. And before that, he was a PhD student at Carnegie Mellon University. So he's got his research interests are in sort of applied analysis and with sort of applications to machine learning. He's going to talk today about adversarial classification, optimal transport, and geometric flows. And I believe Ryan Murray, his co-author on this work, is also here. And so Ryan can help answer questions in the chat. So please feel free to either use the chat or I guess you're happy for people to interrupt you as well, Nicolas, if they want to ask them verbally.
Yeah, so thank you, Matt, for the introduction, and thank you to all the organizers for having me here, and to all of you who are spending your time watching me give a talk. So so today I'm going to talk about basically a connection between three topics. Okay, so the first one maybe is related to machine learning, to learning in general. So that's the machine learning part of my talk. And then optimal transport and geometric flows is the mathematics side of things. Now, the three of them are going to connect in a nice way. I hope that I can convey this idea of how you can see adversarial learning, adversarial classification in particular, more from a dynamic and geometric problem rather than maybe some probabilistic or statistical model. So that's kind of like going to be a little bit of the broad perspective that I will present today. Now, so as Matt already mentioned, so this is based on work with Ryan Murray, who is in here, and he's happy to answer questions in the chat. But of course, feel free to unmute yourself and ask a question if you really feel curious about something. Otherwise, of course, we can wait until the end. I'm also going to mention a little bit of some work that I'm doing with two of my PhD students that is related to this more broader perspective that I will present. Now, so let me just start with two statements that are kind of loose statements, and we're going to try to make sense of them mathematically. This is a little bit of the purpose of the talk. Okay, so the idea of regularization is connected in some way to adversarial learning. Okay, so there is a connection between regularizing and having an adversary. And then specifically for classification, that when you look for decision boundaries, so optimal decision boundaries for your classification, these ones get smoother and shorter when you introduce an adversary in training. Okay, so we're going to try to make to discuss these two statements along the talk. Okay, so of course I don't have to explain this, but when we think about a decision boundary or just the boundary of a set getting smoother and shorter, you should think about something going from something like this to something like that. Okay, so the three topics: adversarial learning, optimal transport, geometric flows. Adversarial learning, I guess the standard iconography these days is a stop sign with a small kind of pixel or a small portion of pixels that have maybe modified conveniently so that your classification rule can go from maybe saying that this is a stop sign to saying that this is a I don't know, some speed limit or something like that. Geometric flows, maybe this is the one more mysterious, especially in this context of learning. Maybe optimal transport is less mysterious, but geometric flows, you have to think about it from the perspective of fluids, perhaps, or if you want something a little bit more kind of a colloquial, just imagine like vinegar and oil and how the kind of interface between these two fluids may be evolving. So just have some images in your mind, but we're going to make a connection between these three things. Okay, so let's get started. So what is adversarial classification? Well, in fact, to give you a definition of adversarial classification, I first have to give you a definition of non-adversarial classification. So just a standard binary classification problem. So the way it works is like this. So you have a data distribution mu. We're going to be restricting our attention to binary labels, so 0, 1. And the idea is you're trying to build a classification rule. In this case, it's just a set in RD. So if you have a point inside the set, you're going to be classifying that point as a 1. If you have a point outside the set A, you're going to be classifying things as a 0. And you want to pick this set or this classification rule in such a way that you minimize some average misclassification error. Okay, so this L here will denote 0-1 loss. So if your classification rule agrees with the true label of your data point, then the loss is 0. Otherwise, if there is disagreement, then the loss is 1. And then you're trying to minimize the average misclassification. Now, it is a standard knowledge, maybe first lecture in statistical learning, that the base classifier, the set that is constructed in this way, is the minimizer of the average misclassification error. And it, of course, it makes a lot of sense. You want to say, well, if you take a data point X, and this point is more likely to be classified as a 1 according to our data distribution, then you should set the label for that point to be 1. Otherwise, you should set it to be 0. This is very intuitive. So we know, at least if we know the data distribution, we know explicitly what is the minimizer for this problem here, for this minimization problem. Well, the previous one. Now let's describe adversarial learning. Okay, so in an adversarial problem, what we have is still we're trying to build a classifier, but now we have to take into account the effect of some adversary that can perturb, modify the data distribution, and therefore you're going to try to minimize now not just an average misclassification error, but a robust average misclassification error. Okay, so the idea is this robust average misclassification error has this form. So if you give me a set or a classifier, this risk or loss is computed by taking a supremum over all possible attacks. And I'm going to describe what are the attacks that this adversary in this model can use. So the idea is that the adversary can take an incoming data point X, Y, so a feature vector X in RD and its corresponding label Y, and it can decide based on those two things to change the X vector. So change the location in RD of the incoming X, and it can pick any point that the adversary wants, as long as this point is within distance epsilon of X. Okay, and so this is essentially what the adversary can do. The adversary can take any incoming data point and shift at least the X coordinate to a new location. In doing so, it can use information about the true label, but again, the important thing here is that it can modify the X coordinate by a distance epsilon. Okay, and so now what we want to do is minimize this worst case scenario, worse in the sense of what the action of the adversary. That's what we want to do as the people who are building the classification rule. Okay, now the question is, in contrast to the unrobust problem, here we do not have an answer for what is the solution to this problem. What is the minimizer A? And it's not, so in this case, the problem, we're going from a situation where we have an explicit solution to a situation where we don't have an explicit solution. But more than that, the problem itself is a min max, and there is no reason to expect that this is something that has any nice properties a priori, that, for example, convexity or things like this. And remember also, this is a problem over sets. So then the natural question is, how do we find a solution to this problem? Now, maybe one strategy for doing this is to replace this risk, so something that is not so easy to handle, into something that is maybe simpler. Okay, so this is the idea of trying to build surrogate adversarial losses, so that perhaps with that surrogate, with that new objective function, then one can proceed. So that's some strategy that people have considered. There's another strategy, although that's not necessarily for the purposes of finding the minimizer A, but it can provide an understanding of the minimum value, and that's using optimal transport. And in fact, we will return to this because this is part of the talk. Okay, but then there's some strategy that allows you to perhaps compute the minimum risk, robust risk, even if maybe you don't know how to compute the minimizer. Okay, now the third alternative, and this is the one that we'll be studying here, is the geometric flows perspective. Now, at this stage, you should think about this, not just, or maybe do not just think of this as, oh, is this a numerical method that is going to work? Remember, our starting point is also to try to understand mathematically those statements that we're connecting regularization and adversarial learning. So, just bear with me and, just let all the questions and all the criticisms, let's wait for the end. Okay, so now again, let me emphasize one more time. Solving the problem without robustness is easy. You just have to compute, based on the distribution of the data, you decide whether you should be classifying things as 1 or 0. And again, as soon as you turn on the adversary, so the adversary has this power epsilon, this is the amount of distance the distance that it can move points to. And the idea is how to build the solutions there. Now, what we're going to do is take a more dynamic perspective. We're not going to be imagining that we have a single problem. You give me epsilon and then I have one problem. But what we're going to be imagining is that we have an ensemble of problems, and we would like to have a way to construct solutions for all problems for all epsilon greater than 0. Okay, so that's kind of the idea. And of course, the idea of geometric flows is very simple. The idea is say, well, you know where to start. You know that the base classifier is the solution when epsilon is equal to 0. And now the question is, how should we be evolving this set, the boundary of the set, so that potentially the flow from then on will produce the optimizers for all epsilon greater than 0. That's the question. So how should we be evolving the boundary of this set? Now, let's just see, okay, of course, in 1D, there's a simple illustration of what we're asking here. So if we, at some point, for some epsilon, we have the optimizer and it has this form, it's just a union of intervals. What we're interested in is how should we be evolving the endpoints of these intervals, or let's say infinitesimally, how should I be changing these endpoints? So that, of course, is the same thing as saying, how should I or what should be the derivative of the location of the endpoints as epsilon grows. Okay, so all right, so then let's go back to the overall general problem we're considering. So minimization over sets, supremum over these attacks that I described earlier, and then we have this objective, this integral over here. So in a sense, we can also interpret this in a maybe more abstract setting. So we have a variable beta, which here is the set A, and then we have some objective function I'm calling f beta epsilon. So this f beta epsilon is the entire, everything including the supremum. So remember, I'm interested in trying to get some equation. So I'm going to say, well, if I evaluate this function, or let's say its derivative or its first variation at a global solution for the problem epsilon, I should be getting derivative 0. This is the first order optimality condition. Now, that differentiation or the computation of this first variation will give me some function, let's say, that will depend on my set or my variable. And what I'm saying is that this function has to be equal to 0, and this should be true for all epsilon. Now, of course, if I'm interested in some equation, how is that all the solutions are coupled when I go over the different epsilons? What I should do is just take the derivative of this with respect to epsilon. Since this is equal to 0 for all epsilon, then I will still have something like that. And this is the type of equation that I'm interested in. So my initial condition, so at time 0, when the adversary is off, I know where is the solution to my problem. That's where my base classifier will go. And then what I have to do is just solve this ODE. So this is just an initial value problem. Okay, so this is kind of the general perspective. Of course, for the specific problem we're interested in, we need to understand what is the objective function. What is this f beta epsilon that I was talking about earlier? It looks like this. And for that, of course, we just try to understand what that supremum is. Well, as it turns out, for this adversarial model or model for adversarial learning that I'm considering here, you have a relatively explicit formulation on what this supremum is in terms of the set A. Okay, so this dA here denotes the sign distance to the set A, and the W0, W1 is the probability of a label being 0 or 1, respectively, and rho 0 and rho 1 are the conditional distributions of our X data given labels 0 or 1. Okay, so that's the interpretation of all this. And let me just explain to you very simple, in simple terms, why is that this supremum is equal to this. Okay, so for that I need essentially to consider 4 cases and essentially illustrate what the adversary is going to do in each of the cases. Okay, so imagine that the set A is fixed, like in here, and imagine that a new data point x comma y comes in. Imagine that the location x is this one here. Imagine that this all these balls have radius epsilon. Okay, so if I have a point like this one, you wonder, okay, will I be able to change the outcome of the classification rule if I change the location of the point x within the ball of distance of radius epsilon? The answer is no, because at this point, the ball of radius epsilon around that point is completely contained inside the set A. So regardless of what you do, you will always end up in a point that is classified as a 1. So you cannot change the classification, essentially. So there's nothing that the adversary can do with these points. It cannot win by changing this point. It doesn't matter. Same story happens over here. If you have a point that is epsilon away from the boundary of the set, it cannot change the label. It cannot change the outcome of the classification, so it's not going to change the loss. But when you are considering points that are within distance epsilon to the boundary, then that's where the adversary can do something. Okay, so and it can do, there are 2 cases basically. So imagine, let's take this point over here. So it's x and it has a label. Suppose for a moment that the label is 1. In that case, the set A would be predicting correctly the label. So because the point x is inside A, and the adversary is interested in making the classifier make a mistake. So that what it should do is, okay, so let me then change this location to a location outside the set, because in that case, I would know that the point would be classified as a 0, even if it had a label 1. So I can guarantee that there is a mistake, or the adversary can do that. That's case 1. Case 2 is, okay, suppose that this is the point x and the label is 0. So in this case, the classifier is making a mistake already. Then the adversary looks at this and says, I don't have to do anything. There is already a mistake. Even if I don't do anything, I'm going to guarantee that there is a mistake. The bottom line here is that the best strategy of the adversary can always guarantee that there is mistakes if it receives a point x within distance epsilon to the boundary, and it cannot do anything else outside. If you use that inside, then you get this formula over here. Okay, so that's kind of the way this works. Okay, so the bottom line is that we have some nice interpretation of what this soup is. It looks like this. And then we can now start deriving the equations, okay? So, okay, let's start with the case of dimension 1, which is simpler to understand. And, you know, we will get some insights from that.
Right, so, Nicolas, can I just interrupt you quickly?
Yeah.
Just a quick clarification question on the chat. Can you just remind us what Ryan's already got in there. So I was going to ask what was the definition of rho again, but
rho is the marginal on x. So it's it's the marginal distribution on the x variable. Mm-hmm.
Okay, thanks.
Okay, so right, so then let's get it started with the analysis for d equals 1, right? So for d equals 1, what do you do? So again, remember, you have already the objective function, and we're just going to take the variation. So the way this works is, of course, you assume the form for the solution, and then you just add a perturbation. So for example, here you're modifying one endpoint, you're adding a delta, and then you say, well, if I change my set, I'm not the minimizer anymore, or, you know, I cannot improve the energy. You use that information to, you know, you take derivatives with respect to delta, say your perturbation, you set things to 0. And if you do that, if you compute the first variation, what you're going to get is an equation that looks like this. And this is characterizing what are the possible endpoints that an optimizer, when your adversary has power epsilon, what is the equations that the endpoint should satisfy, and they look like this. Okay, so this is just obtained by computing variations. Now you can see, of course, this is for one specific endpoint, but you can do this for all the endpoints, and also not only for right endpoints, but you can also do it for left endpoints. When epsilon is equal to 0, that's a special case. I mean, this is a general case of the special case epsilon equals 0, which is the condition that describes the Bayes classifier. Okay, so the Bayes classifier, the boundary is determined by those points for which basically the weighted kind of conditional distributions agree. And that's what is given the Bayes classifier. So that generalizes that condition. And that's the first step. The first step is trying to get the equation of what should the BIs be satisfying. Okay, so we have not related the different sets for different epsilons yet, but that will come in a second. What do we have to do? Well, we just have to take derivative with respect to epsilon. So that's this part that I said, okay, just take the derivative with respect to epsilon of the first variation. That's going to give you some equation. Doing that here is the same thing as what I wrote over here. Just take your derivatives. You're going to get something, and you will be able to solve for dBi d epsilon. So this is essentially the speed at which your endpoints are going to be moving, and you can explicitly write it in terms of the W0, W1, rho 0, rho 1, or their derivatives, and of course the location of BI. Okay, so the conclusion, at least for now, is with this you get a decoupled system of ODEs. Okay, so then this is basically characterizing how is that this endpoint should be changing infinitesimally if we hope to recover global solutions. Okay, and if we hope that this method is able to do that. Okay, so now of course you could ask, okay, are these equations well posed? Well, of course, you need to make some assumptions on what happens at time 0. There could be blow up. In fact, these equations may stop existing, but at least for the time that they exist, they provide some alternative to how to propose potential solutions to the adversarial problem. Okay, so here what we have is, so the condition that we need to guarantee that this is not going to blow up or something like that, at least at time for epsilon 0, is this weak crossing assumption. What that means is that the distribution rho 0 and rho 1, when they intersect, they should be intersecting like this as opposed to something tangential. Okay, so how does that look like, for example, when epsilon is equal to 0? So just precisely at the time when we start this process. So we have our Bayes classifier, we're going to release our boundaries and see where do they go. So the insights that you get from this is, well, that initial speed looks like this. It depends on the difference between derivatives, so rho 0 and rho 1. Here you can see very clearly this non-crossing condition. So this thing cannot be 0, otherwise we would have, this wouldn't make sense. The important point here is that this has a sign. This is a positive sign. In fact, one can see that given the kind of the convention that we have for what is +1 and what is 0. And then the point is that, and this should be pretty intuitive, the point is that what the boundaries are going to try to do is move downhill in the density. And that makes total sense, because if you think about it, you're going to try to push the boundaries to regions where there is less data so that the adversary can give you less of a trouble. Okay, so that's kind of the idea. So just summarizing, so I mean, at least if we follow this kind of a strategy of, we have an initial condition, that's the Bayes classifier, there we have the solution, and we're just going to run these ODEs to try to produce solutions to the adversarial problem. What we would have to do so far, what suggests this analysis, is run these equations. In this case, for this specific model, and I'll get back to other models later, but for this specific models, things are decoupled. Okay, so each endpoint moves in its own with its own ODE. Okay, so at least run this for some time. Now, of course, then the question is, okay, you have this ODE, right? So this ODE solution describe something, but is this something global solution? So is this really what we wanted at the beginning? What we wanted at the beginning was to produce solutions, global solutions to the adversarial problem. So the thing is that these ODEs were derived using necessary conditions, but global minimality is not immediate from that, right? Now, the thing is, of course, the ODEs offer some candidate for who the global solution should be. And then the question is, okay, can we prove that those candidates are indeed global solutions? Okay, so this is the content of one of our theorems. It says, okay, so if you assume that these conditional densities are C1, and you assume that there is not non-degeneracy of the crossings of this, then you can guarantee that for epsilon small enough, the ODE solutions indeed provide global optimizers for the robust classification problem. Okay, so the bottom line is that at least for epsilon small enough, in our paper, we do not say how small it is, but actually one can say something about that in terms of higher derivatives of rho 0, rho 1, etc. But the point is that you know how, that you have the guarantee that at least for some time, you will be able to, just by evolving these ODEs, produce global solutions to the robust classification problem, okay? How do we do this? Because again, here the point is you have some candidates, but then you need certificates for global optimality. So this is where optimal transport comes in. So the first relationship between adversarial learning and optimal transport appear in this in two separate independent works very recently, in fact. And it basically says that at least in the balance case, when the number of, let's say, ones and zeros is the same, or let's say the proportion is the same, so 1/2, both of them, then the adversarial problem coincides with an optimal transport problem where the cost function has this form. Okay, so the proof of this is not so complicated. In fact, this is just, I mean, it's something that follows from some of the general theory on 0-1 cost functions, and you can find this even in textbooks. But it is important. It's an important connection to highlight when you're looking at adversarial learning. So I think that the way this works is people could understand this, but they didn't have this part, and so making the connection is of course extremely valuable. And what we do in our paper is to say, well, okay, so how is it we use this connection between adversarial learning and optimal transport and this optimal transport problem? Well, if we can find a candidate A and a coupling pi for which the objective functions match, we're done. Essentially, that's the couplings here that appear in this optimal transport problem become certificates. So then the question is, if you give me a set A, can I build a coupling that realizes equality here, essentially? So if you remove the mean and the mean over here. So that's really what we do. So now, of course, for the optimal transport problem, we use some information on what is the optimality condition. So in optimal transport, this is known as Node-Schmidt condition. This gives us some clues of how we should be building this certificate plan. And what we do is just, we build this certificate plan, and we can show that this certificate plans make sense for a small enough epsilon, and then for all a small epsilon, we can see that the robust risk for our kind of ODE solution coincides with the cost provided by those certificates. And so in that way is that we prove global optimality. Let me just say that in our paper, so this is what is known, and this is the case of, balanced classes. When we have unbalanced classes, then there is another optimal transport problem. I'll show you in just 1 second. This is something that we did also in our paper. Okay, so this is the form that the general case looks like. So in the general case, when you have unbalanced classes, you actually cannot write this in terms of an optimal transport on the densities rho 0 and rho 1. You have to go to the product space, so the space of RD cross the label 0, 1. In that space, you define a cost function that looks like this for us. And with this cost function, then you can still write, the adversarial learning problem is equal to an optimal transport problem between two measures. So before it was between rho 0 and rho 1, now it's between the data distribution and some modification of the data distribution, which is basically you just swap the labels. Okay, so you look at those two measures, that defines some optimal transport problem, and you have this equality over here. Okay, and then of course the strategy of proving global solutions applies to this thing over here. So that's the connection between these three topics. Okay, so adversarial learning gives us the motivation for all of this. Geometric flows gives us the way to produce candidates. Optimal transport problem gives us a way to prove that those candidates are indeed global solutions. Okay. Now this is in all in 1D. Okay, so global properties of ODEs and topological changes. This is not accounted for in our theory. We cannot say what happens for all epsilon, but we can say only what happens for a small enough epsilon. So are there topological changes? Probably. And in fact, there are some examples. I don't have them here, but there are examples where you can see that this may happen. And so in that case, is there a way to, know that there is going to be a topological change, what to do in that case? And then can you then after that proceed with ODEs or something like that? So that's an open question for sure. And then, okay, other models of robustness, not the one that I just considered. This is also something of interest in 1D. Okay, so there are many questions in 1D already, but at least in like what I have presented so far is this connection between those three topics. Okay, now let's move on to D greater than 1, which is perhaps the more, I guess, interesting from the perspective of learning. Okay, so of course, I promised that I was going to give you geometric flows, but to be honest, like the ODEs that I gave you earlier, okay, I mean, it's D equals 1, so geometry is not so interesting there. And of course, in D greater than 1, you would expect some curvature effects. Okay, so let's just try to understand how curvature plays a role, and then keep in mind how I started this talk. I started this talk with those two statements about what is the regularization that comes in when you use adversarial learning. So this is what we're going to try to get to. Let's just start with a radial example, just for motivation. In this radial example, we have a uniform distribution on a unit ball in dimension D. We impose W0 rho 0 is going to look like this. It's going to be something like, it's going to grow radially, but it's still this density is radial. Then if you have this, of course, you would have W1 rho 1. And of course, since everything is radial here, you expect radial symmetry everywhere. So the base classifier looks like that for this model. And if you had to guess what should be the adversarial classifier for given epsilon, it should be radial as well. So it should have, you just need to determine what is this R epsilon. So then, of course, the idea to try to understand what is this R epsilon is you go in 2 steps. Okay, so you find first order optimality conditions. So these are the necessary conditions. They look like that. Then you take derivative with respect to epsilon, and then you get something that is a little bit horrible. But at least when you set epsilon to be equal to 0, you get a pretty explicit understanding of how is that this radius is going to start changing as soon as you start kind of the process, okay? And you can see that this derivative depends explicitly on curvature, okay? So let's just recall that for a sphere, the main curvature is connected to the reciprocal of the radius. And so this is what we see here. So, okay, so here curvature shows up, mean curvature shows up. Now, of course, for general sets, so if your initial condition is not, I mean, your distribution is not like the one I presented earlier, like with radial symmetry, but in general, then at least formally you would say, okay, so what would be the necessary conditions? Then you would see curvature, the principal curvature showing up. And then you also see some terms that resemble what you had in the 1D case. Of course, you can infer that this nu is normal direction at a point X, et cetera, but it's relatively similar to what we had in 1D. That's the first step. Those are the necessary conditions. Take derivatives, you're going to get something horrible. It's going to look something like this. In particular, you're going to have mixed type PDE. So that means the curvature, of course, is changing. There you have derivatives in terms of space, and then you have derivative with respect to epsilon. So it's kind of difficult to keep track of what's going on here. But at least if our intuition is, we're trying to get some intuition. What are we doing when we're using adversarial learning? Then we can always set epsilon to 0, just see how is that this boundary is going to start evolving once I start robustifying my classification rule. And then you can see that the way that this boundary is going to evolve, at least again in a very smooth, in a smooth setting, will be that that velocity field will look like this. Okay, so you see two terms. The first one over here is the same thing that we had for them in dimension 1. So there is like a drift term that has to do with going downhill in the density function. And then we see another term where curvature shows up explicitly. Okay, so there's two effects, some drift because of density. You're trying to push boundaries so that the adversary cannot affect you because you have less data. And then there's this geometric term, which is the mean curvature term, weighted mean curvature term, which has to do with, well, let's try to make the boundaries smoother and shorter so that the adversary has less room to attack. Okay, so that's the interpretation, and it's just, I guess, nice to see mean curvature flow showing up in these types of problems. So the bottom line here is that adversarial learning, at least for this model, what it's doing is trying to regularize the boundaries, and it's trying to regularize it driven by perimeter. You're trying to make surfaces shorter, you're trying to make them smoother. That's the kind of one interpretation for the curvature term showing up in that term. Of course, I mean, I hope that I don't have to convince you that mean curvature flow is something very important. This is one of the standard kind of examples of geometric flows. It has so many nice properties. It even has good numerical kind of methods for them. You know, so again, I think it was nice to see this showing up in this adversarial learning setting, which it seems is completely disconnected to these two areas. But of course, part of the idea of this work, going again back to the high level, is to build these bridges between these seemingly unrelated areas. Okay, so just one very, very simple illustration of what's going on here. Imagine you have, you know, okay, so this is just the contrast for some distribution that we have. So this thing here is giving me the decision boundary for the base classifier. And okay, what is the effect of this regularization? The idea is that as epsilon grows, the points where you have higher curvature in your decision boundaries are going to get less curved, as illustrated here. And you know, so this is more or less the effect. But this is just an illustration. It's nothing deep is happening here. Okay, so summary so far. We have identified necessary conditions, evolution equations for d equals 1 and d greater than 1. At least the case of d greater than 1, it's more of a formal computation, of course. In 1D, we know that, you know, these equations do produce global solutions, at least locally. And for d greater than 1, this helps us answer those two statements that I started my talk with. Okay, so it does provide some insights as to what is the regularization effect of adversarial learning in this model. Okay, now let me just give you a taste of other adversarial models that I think are interesting, and then we'll wrap up. Okay, so there is another kind of big family of adversarial learning models that is defined as follows. So you still have a problem over sets, let's say, but then the soup inside is a little bit different. So now what the adversary can do is it can start with some data distribution mu, and it can change that data distribution to a new data distribution mu tilde. Okay, so now, of course, the adversary, as before, has limited power. This new distribution mu tilde that the adversary can generate has to stay within distance epsilon of mu, and this distance is measured in some sense here taken to be an optimal transport distance. Okay, so you choose a cost function. Here is where you model your adversary. What are you trying to prevent? So, or how do you model your adversary? You pick your favorite cost, that is modeling your adversary, that's going to give you kind of like this limits to what the adversary can do in terms of changing the distribution, moving to something else. And of course, you're going to be trying to minimize the misclassification error for that, for all those potential mood tildes that the adversary can select. Okay, so this is a little bit different from what we had earlier, although it's related. I'll show in a moment. So for example, if you take the cost function to be something that looks like this, so say this is going to be a cost function on pairs, x, y, x tilde, y tilde. Imagine that as in the first model, we are not going to allow changes of labels. We are only going to allow changes on the x coordinate. So if y is equal to y tilde, the cost is simply based on distance between the points and then maybe taken to the power b. If y is different from y tilde, no, the adversary cannot do this. It cannot change labels. So imagine that I have something like this, and if you take b to infinity, what you get from this model is essentially the original adversarial model, the one I presented at the beginning of the talk. If you send b to 0 with this parametrization, what you obtain is something that is called the strong contamination model, which is a classical kind of robust method in statistics. So this family of adversarial learning models is interpolating between something classical in statistics and the model that I showed earlier. Now, so with my student Chen-Hui Li and also with Ryan, we are thinking about studying the geometric flows that are associated to this problem here. So this is reminiscent to, I mean, at a high level, is similar to what we did for the first model. But of course, the model here is a little bit different, partly because this supremum doesn't have that representation that we had earlier. Now, I mean, before, things were a little bit local in the sense that I just needed to understand what was happening around every point, every potential data point. Here, I cannot do that because my constraint has to do with, on average, I cannot do, or I can do some things or the adversary can do some things to the data. But the adversary can move some points a little distance and some other points a long distance. So in a sense, the equations that one should derive here are, in principle, can be quite non-local. In fact, they will have to keep in mind everything that is happening in everywhere essentially. So they're a little bit, they're no, not a little bit, they're quite different from the equations that we discussed at the beginning. But at least again, at a high level, is the same strategy or the same idea. Let's try to understand what's going on with this form of adversarial learning. What's the regularization happening? How is that boundaries are going to evolve, et cetera, et cetera. What helps in this model is some nice relationship that was studied in quite, in big generality by Blanchette and Murthy in the first paper and later in another paper together with Kang, which basically says that you can characterize this type of term, something like this, when you have a constraint over measures on some Wasserstein type ball, you can write it in this form, okay? And so one can say, well, this looks like a regularization already, but it's maybe not necessarily so interpretable in all cases. But there is something that can allow you to re-express the supremum, at least in terms of a minimization over one variable, one-dimensional variable, which is quite useful. And one can exploit that. One can exploit that representation to, for example, at least in the 1D case, one can get equations that are the analogs of what I presented in the first part that looks something like this. So how should you be evolving the endpoints of your intervals? Something like this. In this case, there's going to be some coupling between the equations. And remember that in the first model, there was complete, things were decoupled. In this case, there is going to be some coupling between them. But this coupling is a scalar function and maybe it's derivative. And then there is some condition that has to stay fixed within the evolution. Okay, so there is, if you like, 2n equations and then a +1 equation because this thing has to maintain along the evolution. So one can use this to derive equations and get conclusions from that. So this is just a little taste of what is happening there. Now, one more thing that I wanted to tell you about is, okay, so everything that I have talked about before is two labels, right? So 0, 1. What about the multi-label adversarial problem? So if you have 3, 4, etc. labels, well, of course, the problem is much more difficult from many different perspectives. Okay, so is there some sort of duality relationship between optimal transport or multi-marginal optimal transport and adversarial learning? Question. Geometric flows, this is even difficult from a, not just forget about machine learning. This is difficult also from an analytical perspective. Okay, so there's so many questions here, but still, I think it's interesting, at least to, for example, develop this relationship between optimal transport and adversarial learning. That's something that my student Jacqueline Kim is working on. But again, the philosophy here is to try to understand what is adversarial learning from a regularization perspective, and potentially coming up with new alternatives for computing things. Okay, so open questions, many. So numerics in 1D even, how can we detect that there's going to be a topological change on the global solution? Can we use information about the dual problem? Remember that we have this adversarial learning, and it has a dual, which is an optimal transport. So can we use the synergy between those two to say something more about, can there be topological changes, when, what to do afterwards, et cetera, et cetera. Theory for higher dimensions, pretty much everything. There is everything that we do in our paper is a formal, but can we at least, for example, say we have global solutions for a small epsilon? Can we make sense of the PDEs that we have there? Are they well posed for a small epsilon, et cetera, et cetera? So there is a lot of things happening there that, of course, we did not answer in our first paper, and are, of course, now open questions. Regularity of minimizers is not necessarily obvious. I mean, at least for epsilon greater than 0, you do not see directly a perimeter or something showing up, and yet things do get regularized. So how to show, or showing something about regularity of minimizers to the adversarial learning problem, that would be a direction for analysis. Multiple classes, everything needs to be done. Other models for robustness, so this has to do with this last models that I was showing you, but you can also imagine, well, I was telling you a little bit about curvature flow because our ball for the adversary was Euclidean. But what if you consider different distances, different models, et cetera, et cetera? So there is many things to explore. And then, of course, maybe one thing that you may be wondering is, all of this that I talked about is, it applies in the context where you have, let's say, the model, you have infinitely data, if you like. But of course, if you have finite data, what can you do? And what you do will resemble what you do when you have infinite data. So there's some consistency question there. There are some directions that we're exploring, but so I mean, it's still in general an open problem, what to do with finite data. Okay, so that's my talk. I hope that I have conveyed this idea that there's adversarial learning, it's machine learning, but there is a lot of room for analysis. If you like geometric flows, if you like optimal transport, these topics do show up, and they're connected in, and I wanted to give you a taste of that. Okay, so with that, thank you, and I'm happy to answer questions.